So welcome to this session, Trash Talk, exploring the memory management in the JVM. Do we have any garbage collection experts in the room? Then you will probably leave because you know all that stuff. If not, then we have 180 slides to go through. Right? You laugh, but I came from 270, so it's so much stuff to cover. So, right, so I tried my best.
Are the slides available?
Yes, I probably will make them available through the conference. Otherwise, just ping me and I will make them available for you. So my name is Gerrit Grunwald. I'm working for Azul. If you would like to reach out to me, you find me on Twitter. Sorry, still say Twitter, hansolo_, and I will respond. If you have questions, if you would like to have the slides afterwards, just ping me and I will send it to you. All right, memory management, right? In the JVM, you can do that later on. In the JVM, right? It's automatic. So why care? Did someone ever care about garbage collection here in the room? Because I never did. I never used to learn about something about garbage collection until I did that talk. And you should care because garbage collection has some influence. It has an impact on application performance. It has an impact on application responsiveness and also on system requirements. And these days where we work in cloud environments, so who's working in a cloud environment here? So you probably know the problems that, we have to keep it small and we don't want to use a lot of nodes and all these kind of things. So garbage collection suddenly is important. At least you should know what it is. In the JVM, this is how it works, right? So we have a stack. This is bound to a thread. And with this, it's more or less local access. That means it's thread safe. And what we store in there is primitives and references. And then we have the heap. And the heap is usually big. And there we store all the objects, right? And this is shared access. So different threads can access the heap. So this is not thread safe. And it needs garbage collection. And then we have the meta space. And the meta space contains class metadata, constant pool information, and so on and so on. This is stuff that contains information for the JVM to work with classes, right? You usually just care about, the problems when you have a stack trace. This is when the stack ran out of memory, or you have the out of memory exception. That is when the heap runs out of memory, right? Metaspace usually are not affected by this. If we take a look at some code, right? This is just simple example. We have a method, we just have a record, we just have some reference, some instances of this person, and then we have a list of persons, and then we print out the P1, in this case, this Gerrit. And if we take a look at that in the stack area, it would look like this. So we have the references on the stack for this thread. So we have the reference for P1 to P4 and the list. And then in heap, it looks like that. We have the objects in the heap and the reference, and they point to these objects, right? This is how it looks like in the JVM. And you see that the list object, of course, points to the references because it contains the objects, right? Okay, this is just for a basic understanding how it works with the stack and the heap. And like I said, garbage collection is only in the heap, not in the stack. The stack grows and shrinks automatically, so you don't have to take care about that. If we talk about garbage collection, then what is it in general? Well, it's a form of automatic memory management and identifies and reclaims no longer used memory. It ensures efficient memory utilization. And it frees the user from managing the memory manually. So if you come from the C++ C area, you have to do all this malloc stuff and free and all these kind of things. You don't have to. As Java developers, we are free. You can just run your code and trust the JVM to take care about the memory, right? Which is a great thing. We have to put them in different phases if we do a garbage collection. I would just try to explain that up front. We'll give you examples later on. So first of all, we have to identify all the objects that are really used, because if you don't use an object anymore, then it's not a live object, it's dead. So you have to garbage collect it. So somehow you have to figure out which objects are live. Right? So this is so-called tracing, identifying the live objects. Then the next thing is, now that we know what's live, we have to reclaim the stuff that is taken by dead objects. So this is freeing, right? We have to free the spaces, right? Or it's also, freeing is the right word here. And then because we have to compact stuff, and I will show you a demo why this is helpful, periodically we have to move objects to compact the heap, right? And this is called compaction, which is clearly a good name. If we take a closer look at the faces, and we start with the tracing, means identifying live objects in the heap, then the principle is like that. We traverse the graph, starting from the roots. We saw that we have a stack frame where we have the references, and we start from there and go into the heap. We point to the objects, right? So we traverse through all these references, and we mark all objects that we reach as a live object, right? That's the idea. If we take a look at the code that we saw before, in this case, I just set the P1 to null. And you see what will happen. So we walk through the P2 reference, we mark it, we find it in the heap, we mark it as this is a live one, I can reach it. Second one, mark it, live. Third one, again. Then we have the list. The list is also reachable. And now it's the interesting part. Even that we set P1 to null, we can reach it from the list. It's still a live object. It is in the heap. Just on the stack, we set it to null. But the reference is still in the list, right? This is still a reachable object, right? You have to keep that in mind if you work with collections, because this is sometimes a problem, that these references are still alive somewhere in the heap. All right. So this is in principle very basic tracing. And then if I set the persons list to null here, then suddenly only these three will be reachable, because then I lost the connection to the list, and then with this I also lost the connection to the P1, right? This is how it works. All right, then we talk about freeing. That means reclaim resources that we have by dead objects. If we take again, so we traverse the whole heap. Now we have to check every object and check is it live or not, because we marked them before. This should be easy, but keep in mind, we have to really check every object in the heap. We can't just check some of them, we have to go through all of them. And then we clear the unmarked objects and remove the marked bits from the marked objects, right? So if we look at the code again, then it will look like this. So persons is already null. We have the three marked objects here. So we remove the first object, and then we remove the list. And then it means, and we unmark it, because then for the next cycle, we have to start from scratch again. That's the idea, right? So this is pretty simple. It gets more complex, just that you get an idea how it works with the stack, where we have the roots, and then with the heap, where we have the objects. Okay, the next step is compaction. Compaction means you have to, like the word says, you have to somehow now that we clutter up the heap, because we add objects, we remove objects, somehow we have all these spaces, we have to just compact it. That's the main idea. And we have two different ways of doing that. So the first way is moving objects in the same area. So we have one area, which is the heap, so we move objects to one side, right? To compact it in this area. To do that, we need a little bit of headroom, because can't use anymore. It's not there. If you try to, you will get an exception. G1. Who knows that one? Probably most of you, right? This is at the moment still the default collector. It's garbage first. This is different from all the stuff that we saw before, because this is a region-based collector. Here, remember, we had these different areas like Eden space, survivor spaces, and then we have the to-nerd space. This one now has regions. And the regions, the size of the regions you see on the left side, they are dependent on how big the heap is. So if the heap is smaller than 4 GB, then it's 1 megabyte, each of these squares. And then it gets up to 32 megabytes. It's the maximum size. It can even be increased at runtime, but then it will stick at that. It won't go to a smaller size anymore. Again, we have Eden and survivor spaces here, but now it looks a little bit different, as we will see. And we have to-nerd space and humongous objects. These are just big objects, right? So they are called humongous objects. So if we start to allocate stuff, then we create an Eden space, right? It's an Eden region within these regions. If it's full, we just create the next one, right? No problem. And the next one. And at one point, we figure out, because if we really take a look at these regions, then because as we saw before, we have dereferenced memory cells, right? So that means only a few objects are live in these cells. If there are just a few objects live, means there are a lot of objects that are dead. They are garbage, right? So we collect the regions that have the most garbage first. Garbage first, that's the idea. So in this case, it's the upper left two regions here. The others are still too full. So we take them and then we move them into a survivor space, right? We just create a new region, copy the stuff over to the survivor space, remove the old one, and so on. You see then over time, your heap will look like this. And then again, if another Eden space is full, we copy it to the survivor space. If the survivor space is full, then we just copy the surviving stuff to the to-nerd space. So this is how it adds up. And then in the end, it can look like this, and it will always change. So this is how the G1 collector works. This is a region-based collector, and all the new collectors work like this. So the old ones, they work as I mentioned before. We have the fixed areas where we copy stuff around, and this one is different where we have the regions. And if we have a humongous object, that means it will directly get this own space. So they are treated differently because big objects, you don't want to copy around and all that, right? Because that takes time. Okay, so that means this is, since JDK 7 update 4, this is in the JDK. It is parallel, partially concurrent, it's generational, and this is a quite good collector. I mean, most of you will use it every day. It's for short to medium pause times, high throughput, lower latency, CPU overhead, still okay. You can activate it as you can see there. It's available on all operating systems. And if the response time is more important than the throughput, this is a really good collector. Pause times must be kept shorter than 1 second, choose this one. And this is also the default collector at the moment. So it's best suited for mixed workloads, large system enterprise systems, responsive, in medium to large heaps. Okay, so it's not as good in small heaps. If you have small heaps, this is not the right collector. So if you work on, let's say, Kubernetes, and you have very small nodes with small heap, don't use G1. Right? This is not the right one for that. Again, you see this is quite complex how it works because it's partially concurrent. And this is very much the replacement for the CMS collector that we saw before. Concurrent mark and sweep was the first edition, and then they figured out it has some problems, and they moved to the region-based G1. But it works very similar, and it's also all the specs are very similar to the CMS collector. So it's not a real-time collector. It doesn't perform well with small heaps, as I already mentioned, but optimized collection time, so it's really fast and mostly concurrent. Mostly concurrent means it's not always concurrent, right? So keep that in mind. Because it's often people say, oh, it's mostly concurrent. That means 99%, but what is the 1%, right? And, oh, I wonder what is that? Give me a second, there's something on my screen. Yeah, so it's the single-threaded execution, avoids potential multi-threading issues that we have here, limited pauses, okay. So G1, nice one. Default collector from JDK 9 onwards. So still at the moment, this is the default collector in OpenJDK. And then this is a very interesting one. It's called Epsilon. Did someone ever hear about that collector? Yes, very good. Because this is a no collector. Right? It doesn't do anything. There's no collection. So you might ask yourself, okay, what's the point here, huh? Well, it's quite useful because if you think about it, if you don't have the collector, then it's just the pure application that's running. So if you would like to test your application performance, this is the way to go. Because usually if you test your application and the collector kicks in and does garbage collection, then this is not really your application anymore, right? So the garbage collector takes time. If you would really like to test your application, then you can test it with this one without having any memory pressure. The problem is, because it doesn't do any garbage collection, you really need to know how much garbage it will produce and how much memory it will use. Because if it runs out of memory, it runs out of memory and that's done. You get an out-of-memory exception. But if you exactly know what you do, create very small services that you exactly know how much memory they use, they could be really fast because there's no garbage collection overhead at all, right? So it's good for extremely short-lived jobs. If you need the last drop of latency improvements or throughput, then this is the one to go. But be careful. You really need to know what you do. So yeah, the best possible performance you get out of it. You can test your application performance, but you run out of memory errors. If you don't know what to do, then you will end in hell. Because if your application just allocates memory like crazy, then at some point the heap is full and then it's full, and that's it. But this is a so-called epsilon collector. It's only in builds of OpenJDK. As far as I know, there's nothing in OpenJ9 that is like this. So that means all the OpenJDK builds, you can use it. Then there is a so-called Shenandoah collector. This was created by Red Hat. And it's quite interesting. I can't go into details. We can go do a whole session about it. This uses the Brooks pointer that I showed you before, and also a loaded value barrier to do that kind of stuff. It's available since JDK 11.09 and onwards. It's parallel, it's fully concurrent, not generational. That's the only one that is not generational at the moment in the JDK. Medium to large heap sizes, pause times are very short, throughput is very high, latency is low. The overhead is a little bit more. It's a fully concurrent collector. That means you just have, let's say, 10 CPUs. If these 10 CPUs have to run your application and at the same time they have to do the garbage collection, then that's different than if you just use all the 10 CPUs to run your application, then you do the garbage collection with 10 CPUs and then you continue running, right? So there's a performance drop, which is not really big, but there is one as soon as you go concurrent. So if you really need high response times, very large heaps, predictable response times needed, then this is a really good collector. If you have latency-sensitive applications, large-scale systems, or highly concurrent applications, then again, this is something you should consider to use. But this is not the only one. There are more. We have some pro and contra, of course. It's mostly concurrent. Again, mostly concurrent. They are very short pauses, but probably it's not a problem. There's no heap fragmentation. It's fast even with large heaps. Pause times that are below 10 milliseconds. That means this is the longest pause that you have for garbage collection is around 10 milliseconds, which is quite fast. It supports compressed references. There's a project called Lilliput where they try to reduce the object headers from 64-bit to 32. If you do that with all the objects, then you end up with smaller applications, right? So, and this garbage collector can handle this kind of stuff. But this is also a project that is run by Red Hat, so it's not there yet. It's non-generational. There might be a generational version in the future, and you have some loss in throughput. Not a big one, but because if you use all the CPUs for garbage collection and your application, of course, there is a little bit of a loss in throughput. It's not available in Oracle JDK, probably because it's a Red Hat product. All the other JDKs support it, but if you are on Oracle, you won't get it. It's, like I said, a bit reduced throughput due to concurrent GC, and it makes use of barrier concepts like loaded reference barrier. It's some kind of a read barrier that it uses, and the Brooks pointer. Another one, ZGC. Did someone hear about that one? Yes, of course. Zero garbage collector. Again, it's a generational one, and I have to say that I copied stuff from other presentations because it's just explaining these things quite good. So we have a young generation, we have an old generation. It's the same idea, so we allocate something in the young generation, it ages, that means it survives garbage collection cycles, and then we move it to the old generation, right? So, and then we have it in the old generation. That's the idea of this kind of layout. It's not really separated like it looks here, because in the end, this is how it looks, right? So we have, again, very similar to the G1 collector. So we have these regions, and we move things around in these regions. Okay. I won't go into detail on that one, because the next collector that I will show you has exactly the same algorithm, and it looks like that this one took some ideas of the other one. So we will talk about that. So this is available since JDK 15. That was the one generational, and then with 21 we have now the it was the non-generational in 15, and now it's the generational from 21 onwards. It's parallel, it's fully concurrent. The non-generational was of course not generational. The new one is. We have a large heap size, very short pause times, very high throughput, very low latency. We have a little bit of an overhead, 10 to 20%, it depends, right? So there's not really hard numbers on that. This is how you switch it on, right? And the generational, as you saw, at the moment you still have to switch on the generational, but this will go away because the old version, the non-generational, will be deprecated in the future. So we will only have the generational ZGC in the future. If you need very high or very short response times, and this is your high priority, this is a good collector. If you use very large heaps, you see 100 gigabyte plus, right? And we talk about terabytes here, it's possible. Predictable response times needed, very good collector for that. And it is already part of OpenJDK. Low sensitive applications, low latency sensitive applications, and large scale system, highly concurrent applications, this is your collector. This is not for everyone. Just keep that in mind. This is a high-performance collector that is, you don't really need to run your small microservice with this collector. It's not necessarily needed, right? Keep in mind that there are other collectors that are better for that. But if you have these requirements, this is the collector to go. Okay, it's mostly concurrent. There's heap stack scanning, which is a little bit, but this is, you can nearly say it's fully concurrent here. It's easy to use. You don't have a lot of parameters to set it up. Supports very large heaps, around 16 terabytes. And you have pause times around 2 milliseconds. That's very short pauses. That's nearly it's nearly pauseless, you can say, right? So you have a little bit of a loss in throughput, of course, because we do it concurrently. You have to use the CPU time for everything at the same time. There's a little drop, but it's not really that big. So it's a great collector. And it will become the default collector in the future. And the non-generational version will be deprecated. So the non-generational, which is currently the one that you can use, will go away. And that leads me to the last one, which is a C4 collector. That's a concurrent continuous compacting collector. And I will go more into detail in this one because this is from Azure. And you see I'm working for Azure. The reason why I mentioned that one is this is already in there for 10 years. We have this collector, and the ZGC is more or less this collector. It's more or less the same. It uses exactly the same algorithm in the non-generational. The generational uses a little bit different approach. But in principle, they are just the same thing. This is part of the Azure Zing JVM. It makes use of the so-called loaded value barrier, which is a read barrier. We use that everywhere. And that's the difference here, because in the generational ZGC, they also have a write barrier that they use for specific stuff. So that's the only difference here. To explain what it does, because this is a totally different approach to that. So we have multiple GC threads that scan and trace the heap, right? So we find live cells and mark them, right? So we'll go through that and mark different memory objects. And that's fine. So what if now at the same time, the application decides, oh, I would like to allocate this memory cell. The collector already passed by that area. So what now happens is there's the LVB, the loaded value barrier, and that leads to the fact that we trigger with the application thread, we trigger this LVB, and this will test and jump. So that means we check, is this cell or this object, is it a reference? If not, it's okay. If it is one, do the jump. Does the jump work? Then it's okay. If not, do something. And I'll come to that do something in a second. So if nothing happens, we just mark it. The allocator marks the object, not the collector. That's the difference here. The same goes for ZGC. They just named it colored pointers. For us, it's bits in the object header, but it's the same thing. The difference here is that suddenly the allocator also does garbage collection work. It marks stuff. And what is the big advantage here? That means now it's marked, and then it passes that, it hands over that information to the garbage collector. So the garbage collector now is aware that there's a new reference that it has to work with. And that's the difference here. That means you only have to access a cell once. You don't have to do that like the remark phase that we saw before, right? So we don't have to. Because the allocator also does kind of garbage collection work here, right? By marking objects. So there's no need to do, the GC don't have to go there and mark it again because it's already marked. That's one of the differences, and that's done by the loaded value barrier. The other thing is if we do remapping, then I show you on top, this is how it works in other collectors. And in the bottom, this is how it works in the C4 collector, and it's very similar in the ZGC. So we have the references that point to the object, to the headers in this case. And now we would like to copy stuff concurrently. So we copy the object, and the next thing that happens is we establish a forwarding pointer, and the other collectors do that in the header of the object. We don't do it. We move this forwarding information in an off-heap page. So it's somewhere, it's always the same place, but it's not in the original object. And there's a reason for that. Because what now happens is the collector starts and updates all the references by using this forwarding information from the off-heap page. On the other collector, it uses the forwarding pointer in the object header to do the same, right? Now, if the application thread at the same time, when not every object reference is moved, tries to access the cell because it's still the old one, right? It makes the test and jump. And that's one CPU instruction. It's very fast. So it tries to access the cell, figures out, oh, it doesn't work. It looks up the one in this fixed area, and then it updates the reference. That's the application thread is doing that. And that means suddenly all the references are fine again. And that's the big difference here. Again, the application thread, so the allocator is also doing some garbage collection stuff that it updates references in memory. Right? This is a big difference, and it gives you a big advantage. The next advantage is, that's what I call the quick release, because the memory, the old object is not there anymore and doesn't contain any forwarding information like on top. There's the forwarding information in the old version of the object, right? So we don't have that. It's in the off-heap page. That means as soon as all the references updated, we just remove the object, no problem. On the top one, we have to first update all the reference before we can remove it, because otherwise it's still references pointing to the old one. In the lower version, we don't have to. We can quickly release memory and reuse it. And that's all part of this low pauses that we have and very fast execution cycle. So the big difference is that the loaded value barrier that is everywhere takes care about that the application thread, once it reaches such a position, it does the test and jump. Is it a reference? Yes. Test it. Jump. Oh, it doesn't work. Look up the reference and update the reference, and then it continues working. Once the reference is updated, the collector doesn't have to do it anymore. So we don't have to touch objects twice. We just approach it once, either by the collector or by the application thread. And that's done by the loaded value barrier. It's this test and jump instruction, and this is just one CPU cycle, which makes it so fast. All right, so this is only available in Zing, so which is our high-performance JVM. It's parallel, it's fully concurrent generational, large heap size. It's the same as ZGC. At the moment, it's only available in Linux. There will probably be a Mac version, but not sure if there will ever be a Windows version. And you don't have to switch it on because it's part of our JVM, right? We just have this one garbage collector. And in the past, we did it in hardware. So Azure built hardware where all the garbage collection stuff was done in hardware. And then we moved it to Zing, which is our JVM. This is more than 10 years ago. I think it's 14 years ago since we did it. So it's the same as ZGC. It's really the same. Response times is very high, using very large heaps, predictable response times needed, and so on and so on. The difference is it's fully concurrent. It supports very large heaps. Pause times, same as ZGC, more or less. No less, we don't have any loss in throughput. The reason for that is that in the Zing JVM, we also have a different compiler, and the compiler produces faster code. If you have faster code, there's not the problem of that you have all the threads working on all things, right? So it means we are even faster than the OpenJDK code with that compiler. The contra, it's only available in Zing, right? So this is not available in any other OpenJDK distribution. But this is more or less the base for the ZGC. It's very much the same thing. You see, this is how it works. It would take too long. I think we are already over time. So just a few words of which one to choose. We have essential criteria like throughput, latency, resource usage. Unfortunately, you can only choose 2 out of 3. You can't just say, I would like to have all of them. So you make the decision, right? And there's a collector for all of this, but there's not one collector that covers it all. So that's something you have to keep in mind. And there's just a graph that I also found on the web, which is not too bad. So it shows you the pause times and also the runtime overhead. And so you can make a decision, right, based on what is your workload, right? If you need very small pause times, then probably C4, ZGC, Shenandoah, good choice. If pause time doesn't really is a big problem, then you go on the other hand on parallel or serial, and in the middle there's G1 and CMS, which is, it's good for most of the stuff, right? So this, and if you choose a garbage collector, keep that in mind. So just don't use anything just because someone does. Just because Netflix does it, don't do it, right? Because there recently was there's something that Netflix published about using ZGC, which worked very well for them. And that doesn't mean everyone has to use it right now, right? Just think about it if you make these decisions. And if you are fine with your application performance, just stick to the one that you have, right? It's totally fine. And with this, I'm done. That have been 180 slides, so I hope it was somehow informative. The original set is larger.